Hello everyone, you're welcome to the first day of the 50 days of tutelage. And we are going to be having math today and we'll be talking about number systems. Before I delve into number systems, let me quickly give you a run through of the things that we're going to be discussing. In mathematics, we have some set of numbers. We have a way we categorize numbers. And I'm going to be introducing you to how you can actually work with these numbers. Then another thing again is that we have some other subcategory of numbers and the way they operate with each other, like prime numbers, even numbers. I'm going to be explaining all of these guys to you as well. Then we'll talk about what are significant figures and we'll deal with a little bit of fraction and so on. So you are in for a ride. Make sure you have your notes with you. You need to take notes throughout this class because you are going to be taking tests periodically as we go on. By the way, you need to watch the introduction video to get acquainted with your tutor. And also, I'm going to like to get acquainted with all of you guys. So I'm going to be communicating with you properly. So let's go into the class proper. We have the number systems. So I'm going to be starting with, we have this list of different category of numbers in mathematics. And then the first one I'm going to be starting with is the what we call the natural numbers. The natural numbers. Natural numbers. Now, what we mean by natural numbers, they are simply counting numbers, numbers that we use for counting. So imagine you want to start the head count of everybody in your classroom. So you start from, let's say, number one, number two, number three, and you keep going for as many students as you have inside the classroom. So that's what like counting numbers are. You have one, two, three, and so on. That is what we call natural numbers. However, some people think that zero is also a natural number, but for the purpose of this part of the world that we are, note that zero is not part of the natural numbers. So anytime you think of a numbers that you use to count, then you're talking about natural numbers. And then mostly they are denoted with this symbol. So if you're working with anything and then you see this symbol denotes natural numbers. So you've learned that natural numbers are counting numbers. So you will need this very, very well whenever you're dealing with some advanced math problem and they specify that, oh, something is a natural number. So you need to know the kind of numbers that you're dealing with. You need to know the kind of numbers that you're not dealing with. For instance, if you say 2.5, 2.5 is not going to be a natural number because it is not a counting number. This is a fraction, a decimal. So you can't use this to count. Now let's go to the next type of number. The next type of number that is close to natural number is what we call the set of whole numbers. Set of whole numbers. And there's no major difference between set of natural numbers and whole numbers. So if natural numbers are counting numbers, 1, 2, 3, 4, and it goes on and on like that. So the only thing with whole numbers is that whole numbers include all the natural numbers and zero is also included as well. So when we say whole numbers, we're talking about all natural numbers including zero. So you should be able to know the difference between when we're talking about whole numbers and when we're talking about natural numbers. The major difference between them is that one has a zero and one does not have a zero. So whole number has zero, natural number does not have a zero. Now let's move on because of time. We have the next set is called the set of integers. Set of integers. And that one is denoted using this symbol. So whenever you see any symbol that looks like this, you know that we're talking about set of integers. Let me write that properly. Yeah, set of integers. Now, what are integers? Integers are numbers that, number one, they include all natural numbers. So let's start with that. They include all natural numbers. They also include the number zero and they include the negative values of all the natural numbers. So what do we mean by that? What we mean by this is that if you say a number is an integer, zero is an integer. So if one belongs to the set of integers -1 is also going to be among the integers. If 2 belongs to the set of integers, then -2 is also going to be in the set of integers. So 3, you have -3 as well. So integers are simply all natural numbers, including 0 and their negative values. So you are coming from -1 billion, 1 trillion, 1 whatever billion that is going to be. You're coming from the negative values of them, and you reach 0, then you proceed to their positive values as well. So integers are just natural numbers that include 0 and their negative values as well. So those are what we call integers. Then now let's begin to talk about the big fish now. Let's talk about the rational numbers. So we have a set of number called rational numbers. So when do we say a number is rational? They usually denote them with somewhat like a Q. Now, rational numbers, just like the way they sound, we can write them as a ratio. We can write them as a ratio, such number P over Q, where Q is not allowed to be 0. So if Q is not equal to 0, that's number 1. And number 2 is that P and Q are integers. P and Q are what? Are integers. Then we say such numbers are rational numbers. Numbers that P and Q, you can write it as a fraction, and P and Q are what? Are integers. So P and Q belong to the set of integers. Belong to the set of integers. So these numbers are rational numbers. For example, you could have 3 over 5. You could have -2 over 7. These numbers are rational numbers. Now, however, saying this -2 over 7 is a rational number is also one thing we need to pay attention to, because sometimes some numbers have repeating decimals, and some numbers have non-terminating decimals, and some numbers have non-repeating decimals. Whenever we have non-repeating decimals or we have non-terminating decimals, we say those numbers are not rational numbers. Those numbers are not what? Are not rational numbers. So what I'm trying to say is that any number that is not a rational number, that such number is going to be what we call irrational number. Any number that is not a rational number, such number is going to be an irrational number. So if a number is not rational, then it is going to be irrational. So now, to see that a number is actually a rational number, because sometimes you are given decimal. If the decimal is not repeating, if it is not terminating, it is irrational. So for example, let's say you have a decimal number. If you press on your calculator now, if you press the square root of 2 on your calculator, so what you notice, so I'm going to bring out my calculator as well and press that on my calculator. So square root of 2 is going to be square root of 2. Yeah. So I got 1.414213562371. Now let's press another square root. Let's say we want to find the square root of let's do square root of 6 now. So square root of 6. Now, if you press square root of 6 as well on your calculator, we're going to go back to that. But let's look at the square root of 2 first. We have 1.41413563371. So what you notice about this decimal is that this is just an approximate value. The decimal still continues and goes on and on like that without any pattern that is being followed here. There's no pattern, no changing, there's no pattern such that you can say that, oh, when you're done with 414, you notice that there's a pattern that is repeating itself. For example, I want you to press 2 divided by 7 on your calculator. So if you press 2 divided by 7 on your calculator, 2 over 7 equals 0.285. 7142857142. Now, so if you notice this, you notice that there is a repetition. You can see that there is 2571, then there is 4. Sorry, 285714. Then you have another 285714. So you notice that this also continues again. Now, based on this repetition and recurring of this, then you say 2 over 7 is a rational number. So 2 over 7 pass as a rational number, and this root 2 is irrational number. So that's how you identify rational number from irrational number. Another example of a rational number is 1 over 3. 1 over 3 can be written as 0.333. So it's a repeating decimal. So repeating decimal is going to be a rational number. So take note, when are they not rational number? That is, when are they irrational numbers? When they are non-repeating, when they are non-repeating, when they are non-repeating, and when they are non-terminating. So this time around, you call them irrational numbers. So now let's move to the next set of numbers that we deal with. The next set of numbers is called the real numbers. So we have what we call real numbers. Now, these real numbers, they are like a mother to all the numbers that we have been discussing so far. So any number you can think of, any number that is possible for you to think of, such numbers are actually real numbers. What do I mean by that? If you think of a number, let's say whether the numbers are rational numbers or they are irrational numbers, then these numbers are real numbers. So 2 over 7, 3.5, 7.222267968.4. Any number you can actually think of, these numbers are real numbers. And we usually denote them with these. So let's quickly do a quick recap. So starting from natural numbers, so you should know what your natural numbers are now. Those numbers that you use to count. Whole numbers, numbers that you use to count, including zero. Integers, they include all the natural numbers with zero and their negative values. Rational numbers, any number you can express as a fraction, p over q, such that p and q are integers and q cannot be equal to zero. So those are rational numbers. Irrationals, they want to behave like they are fractions or some things, but what we notice about their decimal value is that the decimal value is either not repeating, that is, there's no pattern that they follow. They're not repeating some set of numbers over time, and they're also non-terminating, meaning that they never stop. They just keep going and going. All you have to do at any point in time is to always approximate them. So those numbers are irrational numbers, opposite of rational numbers. But when you combine all of these things together, you notice that we have what we call real numbers. Here's also another thing. You notice that in natural numbers, all of them are present in whole numbers. All whole numbers, they are also present in integers, meaning that natural numbers will also be, all natural numbers are present in integers. So you can begin to see which one of them is containing the other guy in this situation. So natural numbers present in whole numbers present in integers, meaning that natural number also present in integers as well. Rational numbers, they contain all integers as well. They contain all integers because you can always write any integer as 3 over 1, negative 4 over 1, 6 over 1. So these are rational numbers as well. So they are contained. The only thing is that irrational numbers, you can separate it out of this entire system of rational numbers. But when you combine all the rational numbers which also already include integers, whole numbers, and natural numbers, when you include it and you join it together with irrational numbers, the combination of the two of them gives what we call the set of real numbers. So quickly, let's go to the next set of numbers. We have what we call the complex numbers. The complex numbers. Now, before I talk about the complex numbers, I think I need to discuss what we call imaginary numbers first. Imaginary numbers. I know most of you before now, if they ask you to find the square root, so if imagine I ask you to find the square root of 4, You will tell me 2. If I had to find the square root of 9, you will say 3. And if I ask you to find the square root of 100, you're going to say 10. But the problem arises whenever I say to find the square root of negative 9. Now, the next thing you want to say is that this is impossible. This is impossible. Anyways, it is not impossible. In fact, the first letter in this place is what we're going to be using to express this. Whenever you have a square root of a negative number, first of all, you need to know that square root of negative 1 is denoted as I. This I represents it being an imaginary number. Square root of negative 1 is denoted as I. So that implies that square root of negative 9 is the same thing as square root of 9 multiplied by square root of negative 1. And that implies that square root of 9, which is 3, multiplied by square root of negative 1 is what? I. So square root of negative 9 is going to be 3i. And this 3i is what we call an imaginary number. The imaginary thing there is the I, that is square root of negative numbers, meaning that it is something that sounds unimaginable. It doesn't sound real to us. Just like you can see, we have real numbers here. So imaginary numbers come from the concept of finding square root of negative numbers. All you have to know, so if I ask you to find the square root of, let's say, negative 25 now, you don't need to stress. It's just going to be what? 5i. That is, square root of 25 is 5, then I is the square root of negative 1. So that is how you deal with imaginary numbers. So complex numbers are now numbers that you can write of this form: a plus bi. Now this I represents the imaginary number, so a plus bi, such that a and b are just any of the numbers that we know, rational or irrational. So for instance, 3 plus 4i is a complex number. As you can see, it has a real part. So this part is what we call a real part. That is, it has a real number. And this entire part is what we call the imaginary part. So for instance, if I ask you now, what is the real part of the complex number 3? Let me use 60 minus 40i. So what is the real part of this guy? The real part is 60 and the imaginary part is negative 40. So you can see that. So the guy with the I is the imaginary part and the real part is what? Is 60. So a complex number usually have the combination of these two. However, a complex number can decide to say, I don't want any imaginary number, and just be, let's say, 60. So what are we going back to now? 60 is a real number. So a complex number is also a bigger set which contains all real numbers. That is, a complex number can be purely real, not having imaginary part, but they can also be purely imaginary. That is, they can just say, I want to be negative 40i. So that implies that it does not have any real number with it. So either it can be purely real or it can be purely imaginary, or you can combine both of them together. That is what the complex number is. So these are majorly the set of numbers that we have. These are majorly the set of numbers that we have. Now, there are now some subsets like the concept of odd numbers, even numbers, and prime numbers. So I'm going to start with prime numbers. What are prime numbers? So basically, to deal with prime numbers, one thing we need to know is that prime numbers are always positive. Prime numbers are always positive numbers. Let's start with that. Now, another thing is that prime numbers, let's call them P, they are always greater than 1. They are always greater than 1. So prime numbers are always greater than 1. And they are also natural numbers. They are also natural numbers. So let's go through that again. Prime numbers are always positive numbers. They are always greater than 1. And they are what? Natural numbers. So as you can see now, so one of the things you should be able to do is that you need to be able to define what prime numbers are. So prime numbers, again, we say they are what? They are always positive, they are greater than 1, and they are also natural numbers. Don't forget, we have discussed natural numbers earlier already. So you should be able to identify what your natural numbers are. So now, what is now the major property of prime numbers? The major property is that they have only two distinct divisors, meaning that loosely we can say they have only two things that can go in them, and those two things are 1 and themselves. So if A is a prime number, can we quickly run through what property that A would have? First of all, we know that A is going to be what? A positive number. So if A is a prime number, A is positive. Not only that, A is greater than 1, and also A is a member of the natural numbers. A is a member of the natural numbers. Now, so by definition, A is a prime number if, after satisfying all of these conditions, the only two things that can divide A are 1 and A. So let's take an example. An example is the number 3. So if something is going to divide 3 and is going to divide it entirely without any remainder, there are only just two numbers that can do that. The numbers are 1 and 3 itself. So 3, let us see if it satisfies all the conditions. First of all, it is positive, it is greater than 1, it is a natural number, and the only two numbers that can divide 3 are 1 and 3 itself. So therefore, 3 is a prime number. A number that looks like prime but is not prime is the number 9. 9 looks like prime but it is not a prime number. First, it satisfies everything. It is positive, it is greater than 1, and it is also a natural number. However, 1 and 9 would divide it, but there's also another number that can divide it. That is what? The number 3. So we now have more than two numbers that divide it. So therefore, this number is not a prime number. So that's that about prime number. Let's go to even numbers now. So for even numbers are very, very easy to understand. Even numbers are just numbers that can be divided by 2. So numbers that can be divided by 2. It's funny that 2 has only two divisors. It is positive, it is greater than 1, it is a natural number. But there are only two things that can divide 2, which are 1 and what? And 2. So that means that 2 is also a prime number. Take note of that. By the way, 1 is not a prime number because you must have two distinct divisors. So let's say if we say 1 is a prime number, it's number one, it even fails already. It is positive, yes. But is it greater than 1? No, it is not greater than 1. Is it a natural number? Yes. So before we even go to 1 and itself, these are not distinct numbers. It already failed the properties because it is not even greater than 1. So therefore, 1 is not a prime number. So the first prime number is 2, and it goes on and on from to 3 to 5 to 7 and 11 and so on like that. So therefore, take note of this guy. So for even numbers start with 2 because 2 can divide 2. So that tells you that 2 is a prime number. It is also an even number. So the only prime even number that we have is 2. So therefore, we will say 2 is a prime number, also an even number. Now, that is even number. Any number divisible by 2 are called even numbers. Now, the next one is odd numbers. What are odd numbers? Odd numbers are basically those numbers that you cannot divide them by 2. So odd numbers are numbers that you cannot what? Divide them by 2. All you have to do is that to know any prime number. So for instance, even numbers can be written as a multiple of 2. So let's say even numbers. This will always represent even numbers. Even numbers 2k, where k is any integer. So now I've already defined even numbers now. 2k, where k is what? Any integer. So any multiple of 2 with the integer will always give us even number. Like 2 times 1, 2 times -4, 2 times -6. So anything you are multiplying with 2 will always give even number. So what is now odd number? For you to have an odd number, so let's quickly do a drill. Let's say you have the number 4. 4 is an even number. If you decide to add another even number to it, the result is also going to be even. So even number plus even number will be even. Now, but here's one thing you can do. If you decide to add just 1 to it, let's say 4 plus 1, automatically it gives you an odd number. If you have even number 8, the moment you add 1, what do you have? You have an odd number. So therefore, generally we can define odd number as such number that are what? 2k plus 1. 2k plus 1. So in this case, odd numbers are numbers that are not divisible by 2. So any even number plus 1 is always going to be an odd number. So back to what I was trying to explain here. Even number plus even number will give even number. But even number plus odd number will give odd number. Even number times even number will give even. Even number times odd number will also give even. So take note of all of these things. Now let's go back to prime. What if I had two prime numbers? Prime number plus prime number, there's no definite thing to say. It can give you a prime number and it can give you a number that is also not prime. For example, if you have 2 plus 3, 2 plus 3 is 5. 2 is prime, 3 is prime, 5 is also prime. But at the same time, I can have 3 plus 7. 3 is prime, 7 is prime, but the result is 10. 10 is not prime. So addition of prime can give you either prime or no prime. However, we are sure that if you have p times p, that is prime number times prime number, it is not going to give us a prime number. So it is not going to be a prime number, because automatically that implies that whatever prime you are multiplying together will always be a multiple of that result. So that's what we're trying to say. So if you say 2 times 3, the result is 6. 2 is prime, 3 is prime, but 6 is not a what? A prime number. So this system of numbers are basically the ones that you need to familiarize yourself with. And so with all of this now, the next thing we want to talk about is majorly significant figures. Significant figures. And these are the major rules that you need to follow whenever you want to deal with significant figures. Let's start with zeros. So for any number that is a zero, zeros, they have a way of being significant and insignificant. So 0 can be significant, and at the same time, sometimes it can also be insignificant. So we'll tell ourselves about the rules to follow to know whether these things are significant or they're not significant. But let's start with other numbers that are different from 0. Take note that any number that is not 0, we call them non-zero numbers. Any number that is not 0 will always be significant. So think of any number, as long as they're not equal to 0, then the number will be significant. So that's rule number 1 to follow. Any number that is non-zero is going to be significant. Now let's begin to talk about zeros. Now there are some things we call leading zeros, and there are some things we call trailing zeros, and there are some things we call intermediate zeros. So let me explain them quickly. What are leading zeros? Leading zeros are zeros that appear before an actual number. For example, 0, 0, 3, 4, 5. These are leading zeros. If you have 0.0062, these are leading zeros. So as you can see here, these ones here, they are leading zeros. Now, what about trailing? Zeros that come after numbers that are not 0. For instance, 3, 4, 5, 0, 0, 0. These zeros here are trailing zeros. Then you have 3.4500. Now, these numbers are what? Are trailing zeros as well. And finally, we have intermediate zeros. Those are zeros that come in between numbers. For example, 330405. These zeros, they are what? Intermediate zeros. First of all, let's settle this once and for all. The intermediate zeros are always going to be significant. Any intermediate zero, they are always going to be significant. So that's one case where they are significant. Now, leading zeros are not significant. Leading zeros are not what? Significant. So take note of that. All intermediate zeros are significant. Leading zeros are not significant. Intermediate zeros significant. So how many significant figures do we have here? Only one. We have one, two, and three. Three significant figures. How many do we have here? One and two, because these zeros are not significant. But in this place, how many significant figures do we have? We have what? We have one, two, three, four, five, six. Six significant figures because these zeros, intermediate zeros, are significant. And lastly, the trailing zeros, they are where we have, some things. If there are decimals involved, then the trailing zeros are going to be significant. However, if decimals are not involved, the trailing zeros will not be significant. What do I mean? In this 345,000, how many significant figures do we have there? One, two, three. So only three significant figures here. But in the case of 3.4500, this is significant, 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 because any trailing zero that falls after decimals, that is, trailing zeros that are in a number that has a decimal point, those guys will be significant. So in this place, how many significant figures do we have? Five significant figures. So these classes are meant to be very, very short, and this is going to be for day one. So day one is mathematics, and we've talked about the number system. Of course, there are many more things about number system, and then I cannot go into so much detail in this particular class. In subsequent classes that we might be having in the future, I'm going to be talking about that. And don't forget to actually subscribe to this channel and share this with your colleagues as well. Share with as many friends of yours that you know. You can also ask them to register for these 50 days of tutelage. There are so many things that we're going to be learning. For instance, today we are done with the class. We're going to be doing physics tomorrow, and then it promises to be awesome. We're going to be talking about measurement and so many other nice things. We're going to be doing chemistry the third day. You have the timetable with you already. I've already shared that with you on the page. So share with your friend, subscribe to this channel, and make sure you always comment whatever it is that you need clarification on. Don't forget, you're going to be writing tests periodically. I'll see you in the next one.